Good morning, everyone. Thanks for being here. Thank you, Terry, and the organizers for a fantastic conference. My name is Yun. I'm a scientist at Google. And there is an icon that says no photography, but feel free. I will actually have QR codes on a bunch of slides that you can explore more stuff in terms of our work. I'm representing work by a broad team that works on healthcare in AI. And we're housed in Google Research, so our primary job is to do research and to find evidence, publish them in peer-reviewed venues in many cases, as well as share information at conferences like this. Disclosure slide, just out of habit from clinical conferences. Now, our work in the area spans many different areas. Traditionally, we've done a lot of work in imaging, which is why a lot of this slide, the real estate, is taken up by imaging-based modalities. More recently, we've gotten into generative AI. Most of the talk will be about the generative AI component, but I'll start off with a bit of our history of how we got into this healthcare space. At the end of each sort of like mini section of the talk, I'll talk a little bit about how we think about impact and how we think the research that we're doing leads towards something improved for patients or users. All right, so where do we start? Well, the year 2016 was when AlexNet came out, just really beating records in terms of image recognition and classification. And when we started, it was sometime in the 2014 or so era, and it was a bit of an open question whether you can repeat something like AlexNet, but for medical images. It wasn't clear at all. There were some studies published actually in that time, if anyone recalls, where they trained their pigeon, like an actual pigeon, the bird, not a robot. They trained their pigeon by feeding it kind of like rewards, like actual seeds and other foods, to distinguish histopathology images of breast cancer versus not. So people trained a bird to do that around that time. But it was unclear, and this is maybe a couple of years before the pigeon study, it was unclear if you could do the same thing for medical images as well, using machines. And so when we first started, we worked with a partner called IPEX, and IPEX had a pretty large collection of teleretinal fundus photographs, as well as we brute force collection of over 1 million labels on that data set. And then we trained the model to detect diabetic eye disease. So this was a simple classifier. End of the day, it was a 2-class classifier, and it got pretty reasonable results. Now, in those days, it was pretty early in the deep learning era. We ended up publishing in the JAMA journal, and that actually sparked kind of like a wave of clinical kind of like AI models and articles in that space. So we did more validation, quite a bit more validation, published dozens of papers in that space, and eventually worked with our partners also present in the first study in Aravind Hospital in India to screen over 500,000 patients since. Now, in the last year, we published a study that we think of as post-market monitoring. And in that study, we determined what was the performance of the model in real life. So not on retrospective data sets, but on real patients that were screened using the AI. And we found a sensitivity and specificity exceeding 97%, which is on par with what we found in internal benchmarks before we had deployed the algorithm. And that was really nice. The other thing we found was a 0% severe plus eye disease being missed. Now, I'm going to pause for a second. Anytime you see 100% or 0%, you should be suspicious. So what's happening here? Well, the model was actually detecting some of these severe plus cases as moderate disease. But in this particular center, the way they operate is that moderate disease is also referred for eye care specialists to look at. And so we did miss some cases in terms of determining severe as moderate disease, but they were referred anyway, and so it was not an actual false negative. So we were sort of like fortunate in that regard. It was by no means a perfect algorithm, but it worked well enough and captured anyone that needed attention across the 500,000 patients. Well, with an asterisk, we looked at performance in about 5,000 sampled cases. Right. Around the same time, we were also working to try and understand what can you do with the same kinds of images. So eye images that you perform scans of, can you detect other kinds of disease, systemic or otherwise? And there was a field that later got a cute name, oculomics. And that field was really about looking at images of the eye. The eye is supposed to be a window into your overall health, and to see if you can detect stuff like diabetes, like liver disease, kidney disease, and everything else. And so we did some of the early work in that space and had some nice research published. Around this time too, we were working with the same kind of like journal editors at JAMA that had helped us with the initial paper. And they were interested in helping to educate clinicians on how do you read these papers, these new papers at a time that were about artificial intelligence, scary sounding words, and deep learning, scary sounding words again. And so we published a paper with them that really just condensed it down into what's really key here in this era is it's not so much the methods and what's in the box, the algorithm that you're using. You need to look at how it's being validated. And honestly, that tracks really well with how the FDA was thinking about things anyhow, but really it was just sort of like really providing a very clear message of how clinicians should be reading these AI papers. All right, so that's all stuff before 2019 or so. Now, at the same time, we had teams working on other areas of medical imaging, so that spans ophthalmology in the previous slide, but also many radiology modalities, as well as ultrasound and a few other things. And we have papers published in reasonable venues for all of these work. And we're pretty happy with kind of like the research progress we were making. We were training specific models for specific indications, and the respective specialties were pretty appreciative of the progress there. Now, at this point, I think we had done enough research work about what we really wanted was to try to understand what does impact mean in this space. Publishing papers was a form of research impact, but we really wanted to reach users to help patients or clinicians. And so some of the stuff we did, so one of them I mentioned already, so that's with the diabetic eye disease algorithm where we screened over 500,000 patients with our partners. And there were several other models that we developed where we found kind of like entities, so these were startups mostly, who were interested in taking the algorithms that we had developed forward with their own validations and additional development to get towards regulatory approval for the specific jurisdictions they were aiming to get to. And from our perspective, that we were very welcoming of that. We would love to see more people using it, and they were taking on the additional work of the validation as well. But more importantly, they were promising to use it for, as appropriate, for screening many patients in many different places. Another thing that we did was to go work with other product teams at Google. And so let's see if the pointer works here. There we go. So on the left here, this is a screen capture of an app called Google Lens. If you're on iOS, this you can access via the Google app on iOS. And what this app does is that it's a way to do visual-based search. So you can take a photo of something, a bag, a shoe, a car, and it uses image similarity-based metrics to try and find images that look like the thing that you're looking for. A key kind of like user need here is for shopping-related journeys. Where you see something you like, you don't know where it came from, you take a photo and you try and figure out, where you can buy something that looks similar. So at the time that we engaged with that team, they were essentially blocking queries, or rather it wasn't working very well when someone took a photo of something on the skin. Often if you took a photo of something on your hand, what it would do is try to focus on the objects on the hand. So for example, if you had a ring on the hand, it would assume that you were taking a photo of that ring, and then find you stuff where there's other rings being featured, even if that's not the thing that you wanted to target in your search. And so what we did was we worked with them to get this image similarity-based feature working much better. If someone takes a picture of something on their skin that's a rash or a lesion or something else, and to look for other photos of similar-looking lesions. So this was not the same kind of models that we were developing previously, but a lot of the same expertise, data sets, and other things we have developed over time were very useful in that process. And later on in the talk, I'll talk about how we leverage the actual assets, the actual models that we've developed in other ways as well by releasing them for researchers and developers to use in many ways. All right, the rest of the talk will focus on generative AI, language models, and chatbots. And before I get into the details, I'll briefly show a slide just to condense it down a little bit. And in a very interesting way, if you think about what a chatbot is, at its core, it's a machine learning model with some inputs and some outputs. Previously, when we were looking at all of these computer vision algorithms, the inputs were images, and the outputs, for the most part, were classification or regression outputs. But here, the outputs are themselves complex. Now, of course, in the actual model, the outputs are mapped to some kind of discrete space, but as far as the user is concerned, the output is a complex sequence of tokens or words. And at its core, if you're looking at text-based outputs, the way it works is autoregressive. It's taking some sequence as input, and it's outputting stuff one token at a time. And so this is deceptively simple, and using this essentially kind of like behind the scenes, you can do things where you create outputs where some of the intermediate outputs aren't meant for user consumption. And we call that thinking or reasoning. And so what's happening there is that in this particular case, there's some kind of input to the model at the top, and there's a really long sort of like intermediate sort of like output that I have truncated, but this is the output that's the internal thinking trace. And then the final output actually shows up. But the internal thinking trace in most of the methods we have right now are basically just the next token prediction. It is just predicting the next word, except that that word is encapsulated by a tag that says, do not show this to the user. This is just for you internally to sort of like think about stuff and figure out what the right output should be. All right. All of the stuff that we are going to discuss next is basically based on this, this one autoregressive-based text generation methodology. And so one of the things we did in this space was to try and understand, can we use this to help clinicians or patients in a clinical workflow of some sort? And the early work that we did in this space was leveraging the New England Journal of Medicine clinical pathologic cases, a very long phrase, but basically refers to clinical cases that are very challenging, often comprised of, kind of like if you've heard of zebra versus horses, more of the zebras than the horses. Not run-of-the-mill everyday kind of like colds and flus, but potentially more severe and more rare diseases. And so we developed this AI, and we wanted to understand if we can use it to solve some of these cases. The way these cases look, these visuals are pages of the cases, so they're actually pretty dense. And in the pages, there's text describing the patient's presentation, how old they are, what their past medical history is, what their symptoms were, and any imaging tests and other tests that they have done. So that's all in the text. In many of these cases, there are also images, but at this stage of the work, we were working with a text input only model. And so we were just using the text part of these cases. And we had a prompt to do the model that is right before the information in this case. And then we provided this in a research study to clinicians to use. Now, how do we set up the study? We had a study where we randomized clinicians, so these were primary care or family medicine clinicians, to two arms. In both arms, they first looked at the case by themselves, and they wrote down what they thought the differential diagnosis of the case is. If you're not familiar with differential, it's basically a ranked list of possible diagnoses that they are considering for that case. And they could provide up to 10, although I think people tended to provide something more on the order of 2 to 5 diagnoses. So in both arms, they did this sort of like first unassisted based diagnosis, just looking at the case. Now, the next part is a bit different between the two arms. In the first arm, what happens is that we ask them, hey, we've provided an AI for you to use. You can use it in any way that you wish. Please don't ask it for information that's not in the case, that's going to be hallucinated, it's not going to be true. Many of them did so anyway, but there was instructions given. And then they were supposed to, after using the AI, then write down their diagnosis. In the other arm, what happened was that they were asked to use internet search or any other textbooks or resources that they wish, and then write down their diagnoses. And so essentially what you're going to see on the next slide in terms of results are first the unassisted results, followed by the assisted results in two different modes. All right, so walking through results, the y-axis here is the differential diagnosis accuracy. And this is captured in terms of, is the ground truth that was in the original New England Journal case captured in any of the diagnoses they listed. And then the x-axis here is the position of the diagnosis. And so it always goes up and to the right. And the blue line here is unassisted. So you're seeing actually pretty modest numbers here, starting from about 15 all the way up to slightly over 30. And so these are low numbers. It sounds very low, and it is low because these are very challenging cases. And remember, these are unassisted clinicians who haven't looked up any information at all. Now, once you provide information where you are allowing them to use searches or textbooks, there's a pretty big jump of about 10% across the board, across all positions. And that's really good. Now, once we provided them, on top of that, the AI provided diagnosis, in the physicians in that arm did even better. Now, one thing you'll notice is that the 10% gain is mostly in the latter part of this, meaning that they were providing both longer diagnoses, and it was the longer diagnoses that started to capture more of the correct answers. Now, the elephant in the room is the line in red. The line in red indicates what happens if you use a slightly different prompt, but you just ask the AI to provide a diagnosis without any human intervention. And in this particular case, for these challenging cases, the AI actually had the highest performance overall, again, with more accentuated differences towards the end. Now, what's the takeaway? Replace doctors with AI? No. Definitely not. I think the takeaway here is that when you have a situation where someone has done all of the work, done all of the workup, provided all of the tests, and you put them all in a nice summarized text paragraph, now you're basically testing an AI's ability to extract associations and understand the input, and then predict what are possible things that are correlated, basically pattern matching with that particular input. And in those cases, this does really well. I think that's the takeaway. Now, clearly, if you think about a real clinical scenario, that's not what's happening. The patient does not walk into the exam room, sits down, and say, "I'm a 50-year-old male. I have a history of whatever," and then they start giving you all of the information you need to make the diagnosis. That does not happen in real life. So one of the next things we did was, can we get around that? And this was a little bit early in the journey, so we had to do a bit more of our own tuning. But at that time, the way we did the tuning was that we had this sort of like virtual simulation-based environment where we had a model that we were trying to train, and the model was supposed to go ask questions to a patient eventually. And so the model was asking questions to a simulated patient that was role-played by another AI. These days, we'll call that a multi-agent-based system. Those days, it was just two different AIs being role-played against each other. And so we role-played it, and then we did tuning. And so eventually, the model was able to take the medical history from the target audience. And we studied this in another randomized study, this time with patient actors, and in an OSCE-style study. And then in this case, we used a virtual chat-based interface, which means the AI was using text inputs, and the patient actor was using chat inputs as well. And we had a randomized arm where there were real physicians doing this kind of like the same study. And because it's all text-based, it really made the randomization a lot easier, because it was much easier for us to blind the user, the patient actors, to whether they were talking with an AI or a physician. And so we found, and this middle plot over here is a very similar plot to the previous slide, but with the numbers a lot higher, because these were OSCE scenarios that we created, or slightly more representative of the real world as opposed to challenging cases. And again, you see kind of like a very similar trend, where if you see performance for physicians versus for the AI, there was quite a big improvement over here of about 20%. So that's the sort of like result in terms of a diagnostic accuracy. And in addition, we asked specialist physicians, specialists selected on a per scenario basis, to assess the transcripts and the outputs of the AI or the physician, and then in a blinded way score them across a few different axes. And we saw again that the accuracy was better, management as well, escalation was about similar. And then in addition, we asked the patient actors who were interfacing with the agent, whether it was an AI or a physician, and in a blinded way, they were rating overall whether they felt that the agent they were speaking to was more empathetic and so forth. And again, they scored the AI better. Now, part of this is really because the AI is not going to be tired. It's going to be very happy to inject very nice language into its responses and provide very long, detailed responses. This is part of kind of like the reason we're seeing in many of these studies kind of like empathy or perceived empathy scores to be a lot higher when someone's talking with an AI. All right, so a lot of that was done using kind of like very broad multi-specialty kind of like cases. Another thing we did was to collaborate with a few different institutions to examine the performance across a few different specific subspecialties. And each of these study designs are very slightly different, with somewhat similar kind of like takeaways from each of these studies. And the references are here for those who are interested. All right. Now, as we progressed, we started moving beyond this single AI-based kind of like approach. And some of you heard in a previous talk at the conference, how the agentic world is coming for us. And in this case, this was again kind of like a different setup where there's sort of like different agents doing different things. And I think part of the reason we wanted to do this was because we needed these models to be doing different amounts of compute for different kinds of tasks. So in this particular example, one of the advancements we did was we had an agent that was responsible for the dialogue with the patient or patient actor. We had a different agent that was processing the dialogue every few turns. It was summarizing things, trying to figure out like what things could be, and then looking up the treatment guidelines for them. And then yet another sort of like step there was summarizing those guidelines and providing kind of like a next steps. And this is happening kind of like asynchronously from the rapid fire patient kind of like agent-based conversation. And so what this lets the sort of like system do is to provide compute that's doing stuff that needs to process an entire guideline-based document and separating that from stuff that just needs to process the patient input, which is usually just a few lines. Another advancement we did in this space was to try and consider what is actually happening in a patient-doctor conversation. And based on human-computer interaction and you know, kind of like even just talking to doctors, we know that if you talk to a doctor with a new concern, what's usually happening in the first sort of like part of the conversation is that you have the physician asking the patient questions to try and get a sense of what's going on. So there's a lot more information flow from the patient to the physician in that first half. And then later, as the physician gets a better sense of what's happening, they may then kind of like start provide more information back to the patient. So the information flow, the net information flow, it's a little bit different in different phases of that conversation. And so what we then did was to, within the kind of like AI system, we had it work in terms of having discrete phases. So information collection phase versus figuring out the diagnosis versus conveying information. So that state-based system was something you could engineer directly into the system. Now, to be clear, a state-based system does have its flaws. One of the flaws is that if you get towards the end of the conversation and you say, hey, here's the diagnosis, here's what you should do, and the patient goes like, oh, I'm sorry, I forgot to tell you this one very key important thing, that messes up the state-based system if it's a unilateral flow. So you do need to be able to handle that kind of thing. So there's pros and cons to engineering that kind of explicit flow as opposed to relying on a model to handle that elegantly itself. Another thing that we did was that when we looked at the overall sort of like system and how information was flowing, as well as where the risks came in, it became clear that the risks for a system or AI system that is interacting with a patient, the risks really come in when the AI is providing information back to the patient that may affect their decisions or what they're going to be doing next. And so if you look at that from a kind of like a risk or a safety-based sort of like lens, then you can imagine that it's relatively safe to collect information from the patient and with the right validation, summarize that information. But then there's more risks when you start conveying, hey, this may be X or Y diagnosis, here's what you should do next. So one of the things we did here was we tried to study what would happen if we then constrained the agent or trained it not to provide the information back to the patient. And then in this overall setup, we then had it summarize the information and provide that to a physician who then signs off before that final information is given back to the patient. So there was one kind of like guardrailed system that we developed and tried to study. All right, and how do we think about impact in this space? Well, one of the things we're doing now with our partners in Beth Israel Hospital in Boston is to study this in a prospective setting. And all of the previous work I've discussed were work where this was done either in a completely retrospective setting with no patient involvement or with patient actors playing the role of specific sort of like synthetic scenarios. And so here what we're doing is to, in a prospective consented sort of like setting, with real patients that have real concerns that they're trying to set up appointments to see the doctor about, we're examining how they then interact with an AI agent and documenting the learning. So the study has started and we're doing analysis right now. All right, so that brings us to the end of kind of like one part of the Gen AI work, which really focused around this like conversational patient physician kind of like based interaction and how it can help there. The next few slides will talk about how we are exploring some of the capabilities. And some of this will feel like it's rewinding a clock, and it is, because some of this category of work actually goes back in time a little bit to back when the technology hadn't advanced to that stage yet. So one kind of like blast from the past, and this is really small. I think the main key thing is that if you look at this plot, the x-axis is a measure of time with months on the x-axis. Y-axis is a particular benchmark, in this case MAC-QA, but you see this for a lot of benchmarks. And what happened here is that you see that there was steady progress, and this looks a little bit like LXNet actually. There was steady progress for a while, and then over the span of less than a year, there was a dramatic leap in performance from kind of like 30s or 50s all the way up to the 90s in terms of performance for this benchmark. And this was one of the times when, as we kind of like improved the base models that these large language models are based upon, the base models started getting much, much better at answering these medical questions. In addition, with some light tuning, the performance increased additionally on top of that. Another thing we did in this kind of like time period was to try and figure out what are the right frameworks to use to evaluate these models. And one of the frameworks was around fairness and equity. And one of the learnings here, I would say, is that it wasn't so much as about the specific models that we were evaluating where the details of the performance matters, X or Y percentage. What was really important is that we found if you ask a person if there's bias, sort of like, or equity potential issues in a particular model response, the person they ask matters a lot. If you ask a medical expert, there are certain kinds of things that are considered kind of like bias-related factors in that particular specialty. For example, right now, race is considered, a really important factor to try not to incorporate into decisions around kidney function. But if you ask an equity expert, they're looking for societal and structural issues that they're trying to watch out for, and historical kind of like inequalities and so forth. Now, if you ask a layperson, they yet again have a very different sense of what they believe to be bias or equity-related issues. So if you see studies, looking at and assessing for bias and equity, just pay special attention, I think, to who they were asking, who their raters were. Were these kind of like medical experts, equity experts, and were they lay people? And if they were lay people, what ages and what generation are they from? Like, what do you think these raters were looking for? So when you do these assessments, just watch out for who it is that is answering the question. Another thing we did in this space was as we shifted more towards the Gemini era at where I work, we started to investigate whether the Gemini models were as capable as previous models at healthcare-related questions, and we published a pair of reports that investigated different kinds of capabilities there. All right, and some of this were actually predecessors to the work that you saw in the previous section around the clinical conversations. All right, so this section, I'll keep it fairly brief, but was around understanding if we can use wearable data to inform kind of like healthcare-related questions. For example, if the patient is thinking about why are they tired, knowing that they slept 2 hours less every day in the last week, or if they're traveling to a conference and struggling with the time zone, could be quite helpful. And other things that we explored in this space was to understand what user needs were and how would you engineer a agentic system to take care of different kinds of needs so that you can specialize each agent in a specific way. Another thing we did in this space was if you look at the wearable data, a lot of it is recorded on a per minute time basis. And so on a per minute time basis, you often have missing data. And that happens often when a person has taken off the device to charge, or if they just forgot to wear it that day or some other reason. But missing data is a huge component of working with wearable data. But interestingly, with these modern systems, you can actually train the architectures, the encoder-decoder architectures in such a way to incorporate and understand missing data. And indeed, it's actually part of the way that we train them to understand representations. All right, and how do we think about impact in space? Well, part of the wearable stuff is work with the Fitbit kind of like product, and so we worked with them to incorporate these learnings into Fitbit products. And there's several links over here. Some of the products are a personal health coach that understands your personal data, whether it's from Fitbit or elsewhere. And then we also released a kind of like experimental feature called Plan for Care, which is meant to, I think, in similar spirit to the guardrailed agent we discussed earlier, to try and take in information from the patient and before a doctor's visit and help them prepare questions for the doctor so that they're much better prepared and able to advocate for themselves during the visit. All right, the last section will be about how we took the assets and models and data that we've developed and tried to help the community using these. And one of the things we did is to create this sort of like suite of models called the Healthy AI Developer Foundations, where we have a number of different models that are available. Some are image-based inputs to get kind of like embeddings or representations of the images. Some are generative AI models that can take images and or text as input and then output various things. Now, one thing about kind of like text inputs, one thing that was at least interesting to me when I first kind of like went into the space, you can work with kind of like chemistry-based inputs as well, because you can actually represent many of these molecular structures and other things using text, and then feed the text into the model, and if you tune it appropriately, it can provide meaningful output. So one of the work in that space, and we've released this model, it's called TX Gemma, and you can give it a whirl if you are interested. All right. Our kind of like flagship model right now is something called MedGemma. It's built upon Gemma 3, and it follows the same recipe that Gemma 3 was developed using, except that we used a lot more medical data in the space. And so what will happen is that the vision encoder part of MedGemma understands medical images a lot better than typical kind of like broad purpose language models. And we've released kind of like a few different sort of like size variants of MedGemma, as well as just the image encoder piece of MedGemma called MedSiglib, if you're interested in just working with the images and you do not need a text-based output. Pausing for photos, and okay. And we've also released a number of kind of like inspirational demo apps that some of our great engineers have developed. And these demo apps really outline kind of like just inspirational things of what people may be able to do these technologies. Pausing another second for photos. Okay. And here's one example. The actual website has the animated version, but I'll show a quick screen capture over here. And in this particular example, what you're seeing is that in purple is actually shown kind of like the thinking trace, and this is only shown once just for brevity reasons. But what's happening in the conversation is that there's a simulated patient, in this case role played by a Gemini model, that is sort of like, that has a scenario that it's running through, and it's providing information to an intake agent that is role played by MedGemma. And so this is a Gemma model that's been tuned to be a intake agent that's collecting information essentially from a patient. On the right over here, it is essentially in real time summarizing the information that's collected so far. So you can imagine that technology like this can be used exactly to build some kind of intake agent, a little bit similar to the guardrailed AMI work that I discussed earlier, as well as the plan for care, but this will be built using open models that other people can take and use. Another sort of like concept app in this space was to try and understand if we can explain medical reports to a more layperson kind of audience. And in this case, what's happening is that there's a real chest x-ray and a real report. This is not generated. And what happens is that it's detected which sections of these reports are kind of like concepts that people may be able to ask about. And in this particular concept, you can click onto this and you get kind of like explanations of each section of the report. All right, so what does the impact look like in this space? One of the first metrics that we were tracking over here is, after it was released, was were people aware of this? Were people downloading it and using it? And I'm pleased to announce that there's been over 1 million downloads of the model so far, and so people do seem to be aware of and testing it, and some members in the audience, I think, have helped us benchmark these, so thank you. On the right over here was an interesting post. So we uploaded the models early, I think it was like July last year. Mid-July, about 10 days or so after we released, we got this outreach on our forum from a startup called QMed. And QMed works with the Malaysian Health Ministry to help them provide a platform for Malaysian kind of like clinicians to look up the guidelines in kind of like a natural language way. One mental model for this would be something like open evidence, except that it's specifically catered to that country's clinical practice guidelines. And so QMed already had a stack where they had a text input-output sort of like version of this. They could ask about questions and so forth. And they basically reached out 10 days after we launched to say, hey guys, thank you for releasing the model. We've incorporated it into our stack. Live people are using it. And we went like, what? Like 10 days? That's unusual. Turns out what they were doing was that the tech stack was already working for them. What they were using the model for was to generate a number of sort of like captions or descriptions of images that people were uploading. And those images are then used as part of text input into their regular stack so they can then retrieve the right guidelines. And so it's kind of interesting that folks were able to sort of like take these open models, build upon them very, very quickly, and then get towards applications that real users were using to help inform patient care. So we're very, very pleased to see that, and a few other folks have reached out around kind of like their successful applications as well. All right, to conclude, so computer vision models were very, very popular about 10 years ago. If folks have tried to attend NERBs and basically they had maxed out attendance, you'll know what I mean. But these were very popular 10 years ago, and folks were able to then get them working with high performance, and they're starting to really help in a variety of different fields. Radiology is one, but also ophthalmology, and a few others have gone pretty far in terms of like regulated sort of like devices in this space. And we have sort of like helped with our partners screen a number, over 500 million patients for diabetic eye disease, and also for certain other models licensed them to use for other indications. Generative AI is very, very different. And one thing that's worth keeping in mind is that their capabilities are improving very rapidly, even over the last 2 years. And so every kind of like quarter or 2 years, seeing kind of like a leapfrog in performance, whether it's efficiency or performance or something else. And they're enabling a kind of capability that the traditional computer vision models are not capable of. And so keep a sort of like eye in that space. And we think that generative AI can be really helpful for many users. And as we develop these things and kind of like do the consented studies as needed with IRB oversight and patient consent, we are trying to understand where the gaps are and what can be done to fix those gaps. And with some of the advancements that we've developed, we are releasing models for people to use. They are free to use. You can use them for research or commercial purposes. The only restriction there is that you do not make Google the manufacturer of a medical device by using that. So don't stamp a label on it and call it a medical device. Do your own validation, tune on your own data set for your own purposes. And with that, I conclude my talk. There's 2 QR codes there. The left side goes to a Google Scholar profile with a full list of, I think, about 300 papers now. And on the right side is a QR code going to our open models. And it has links as well within that page to a developers forum where we can ask questions and email lists as well. Thank you for your attention, and I welcome any questions later on.